I know about this work about the same way as everyone who is looking on the slides. It is not what I'm doing every day, but they take a modification of wet halide perovskite surface with or without some defects, and they want to compare two categories. First category, to compare presence of absence of defects, and second, they want to compare predictions of the Redfield dynamics and surface hopping dynamics. I was glancing on the previous version and asked to just give some very brief comment looking on the screen, and BaoLiu did the explanation how he creates initial conditions. So instead of our oscillative strength, code they import dielectric constant calculations directly from Wattband, select several transition energies as initial condition. So here in this slide, he's showing Redfield dynamics on the bottom, and on the top, it is these same parameters and processed by fewer switches surface hopping, which gives relaxation dynamics of the same order of magnitude, but quicker, about 2-3 times quicker. And this their comparison is not constant. The difference is bigger for low energy excitation, and agreement becomes better and better for higher excitations when there are multiple channels. What is the difference? Just looking at here, they do dynamics only for 2 picoseconds, and they do it in a linear scale just by the nature of surface hopping method. Redfield does it by several orders of magnitude, so it is in favor of Redfield. In favor of surface hopping, they carefully treat non-adiabatic couplings at each time step as an independent data. So they avoid doing average Redfield tensor, and they take into account quick changes of the non-adiabatic couplings at each time step. And it may or may not give some favors. Therefore, comparison is good. In Redfield, one does one trajectory, one electronic trajectory for certain initial conditions. In surface hopping, these figures are adding together several hundred electronic trajectories. If one would look on the individual trajectory, it will be very choppy. It is like no change in energy, then jump, no change in energy, another jump. Sometimes jumps go up in energy. So I think both methods complement each other. Here, to my understanding, is an attempt to select different initial conditions. Here is an attempt to compare the rates of relaxation at different initial conditions, and I hope at the next iteration, BaoLiu he will put this data in the graphical form that one can explore if this data fit the energy gap law. So there are data for energy difference, and there are energy data for rates in both Redfield and surface hopping. And it is just one little step to go from this table to graphical information and check if which of the methods fit gap law better or worse. My understanding, this table includes the same type of information, but for electrons. And I'm not sure about which modification of the system, because with or without defect. So in the ideal world, this table should be done for each of the modifications of the model at least once for room temperature, maybe for several temperatures. Here, I believe BaoLiu is extracting the recombination rate by identifying the element of radical tensor corresponding to recombination. I'm not sure if it is done correctly. This maybe yes, it is big. Like here is 7 to minus 7, and nearby those are 3 minus 4 and 3 to the minus 4. Yes, it seems reasonable. And then there is an attempt to compare this number of the recombination rate combined into a single number of the radical tensor with surface hopping simulations for recombination from LUMO to home. Since time interval in the surface hopping method is limited, one cannot gain the full recombination, but one can explore initial steps of these dynamics and then use the slope as a prediction of the recombination rate. And here, I think there are 4 modifications with vacancy, interstitial, and something made to it. Okay, if I would be the prime presenter, I probably would start from this slide explaining the geometry of the models. So vacancy of iodine, additional iodine, and additional lead. Yeah, this slide should be the first one, the next one should be the second one. Here are the projected density of states, and diffracted models are expected to have smaller gap and slower relaxation, but quicker recombination. We can scroll back and check. So one expects slower relaxation because of subgaps in the band, but quicker recombination because of overall band is small. Here, to my understanding, is the momentum dispersion for these models, showing how this states inside the gap are forming and how the Fermi energy is changed. And I believe one needs to work more and have graphical comparison of the gap flow before making conclusions. So if there are questions to this presentation, please feel free to type or verbally mention, and I will try to forward it to the author who generated this data. As well as we can take it as an inspiration and do similar work in the near future.
We go back to the table. Now you show the right view. Yes, the first one. Yes. So what are the red colors?
Red numbers are relaxation time. My understanding that by dividing 1 over 0.44, one will get 2.2. So all this relaxation time. And call it 1 over each. One. Here is the relaxation time in surface scope.
Also, why this model is so special? Because we see these two numbers are pretty close, right? But this is not the case for the next table.
Let's forward the question to the author and try to analyze. So for addressing this question with a little bit more details, I would be happy to look at density of states and spaghetti plot. In case the quantum orbitals are space dense, if there is a continuous band, then methods should coincide better. If they're sparse, it could be noticeable dependence on the method, because this offset of orbitals changes over time, and it could be very slow in Redfield, because for most of the time, in average, there is a big offset. But for one short period, they cross, and at this point, you will not notice it in the average energy, but this single crossing is sufficient to dump all population from higher state to lower state. So for continuous dense spectrum, we expect better agreement. For noticeable subgaps at high temperature when they oscillate and cross each other randomly, we expect some error, and surface scoping is expected to work better this limit. Here is asking which one provides better results, Redfield or surface scoping? Why do we need to use FSSH method? Oh, it was question only to me. Others didn't see. So the FSSH method. Well, I have a cynic reason that I probably shouldn't record. FSSH method has other authors, and we need to give credit to them. Redfield method was developed here in group, and we do not need to credit anyone. There are pros and cons in both methods. Both methods are substantially, electron dynamics calculation is substantially quicker than computation of couplings. So the major bottleneck for calculations is getting couplings. But supposing the couplings are already done, Redfield is like several thousand times quicker than the surface scoping, or even better. So surface scoping single run will take from a couple of hours to maybe the whole day. One doesn't need a cluster, one can do it on a laptop PC. And Redfield works in like half a minute. So simplicity and quickness is the strength of Redfield. The strengths of surface scoping is that there are limits, there are regimes of dynamics when it works better. So Redfield in the implementation, you have it in the group, uses more approximations. It's more approximate. It doesn't mean it is worse, but it is approximate means quicker and efficient. But original way in the surface scoping and density matrix dynamics were developing simultaneously, and they exchange ideas between communities. So original dynamics was always from like 1925 to 1965 was made only theoretical and only by density methods. Then there were, upon advent of computers, even some simple computers in late 60s, beginning of 70s, there was an attempt to go from density metrics to only diagonal methods, to only populations, and connect it to explicit nuclear dynamics. So it's John Towley was doing it for very simple models like H2 molecules. And then his method was found to be efficient for these more and more powerful computers for bigger and bigger systems. But at some point, it was an observation that all bells and whistles of surface hopping, statistical average, depending on the amount of trajectories, is not needed. One can get results which, in certain limits, agree by substantially cheaper effort. So, and can be explained and justified based on initial foundations of the open quantum system through density metrics. So it is complementary methods that serve similar role with pluses and minuses. Like if one fails, one can use another one and opposite, or one can run both and compare. Okay, does it address your question? Okay, are there more questions to BaoLiu? Thing, and let me stop sharing, and we'll thank all authors of today's abstracts for and all contributors to discussion. Do we miss any volunteer who wanted to present today? Probably that's not present even if there are volunteers and try to do things next week. Some of us need to prepare the finals, including me, not taken by giving. And meeting is complete. Everyone is welcome to depart and disconnect. Stay here. We just need to quickly chat.